Computing gradients back propagation. Already we have seen X input W1 weight 1, W2 weight 2. This is hide layer. This is Y cap is the output, target output. Z1 is the hide layer. J of W is jth weight. Partially differentiate of jth weight W with respect to W1. This one partially differentiate with respect to this. Okay. Sorry. Please consider this is dou. So dou J of W divided by dou W1 equal to dou W of J of W with respect to the first this one with respect to dou W is that convolution with this differentiate again this one. This differentiate with respect to this differentiate with respect to this, that is Y cap, dou Y cap. Here dou is at 1 with respect to this will differentiate with respect to this. That's why back propagation coming next. Okay, this partially differentiate dou J of W with respect to dou Y cap. Dou Y cap partially differentiate with respect to dou Z1. Dou Z1 partially differentiate with dou W. This is the thing. Okay. So this one happening here, this one happening here, this one happening like this. This one, this one, this one. Okay. So say do J of W with respect to do W1 equal to do J of W weight with respect to Y cap target output. This partially differentiate with respect to dou Z1. This one partially differentiate with dou W1. All are convolution. Okay, multiplication. Repeat for this every weight in the network using gradients from later layers. Back propagation. Computing. This is computing gradients. Repeat for this every weight for each weight. For example, 1, 2, 3, 4 up to J. So iteration. Repeat loop. Do every weight in the network using gradients. From gradient means this is the gradient. So gradient from later layer. Neural networks in practice optimization. training neural networks difficult. Training neural networks is difficult. Neural network to be trained is the difficult. Loss function can be difficult to optimize. Loss functions can be difficult to optimize. Remember, optimization through gradient descent. This is the gradient descent. So multiply with mu, then minus with w. So doing like this up to this value already mentioned 0, 1, 2, sorry, 3, 4, 8, 2. No particular. So when it will come, that time j equal to j0, j equal to 1, j equal to 2, j equal to 3, like. So we have to keep in mind always this one. W tends to getting from W minus mu dou J of W with respect to dou W. Loss functions can be difficult to optimize. Loss functions can be difficult to optimize. Remember, optimizations through gradient descent. How can we set the learning rate? This is the learning. How we set the, how can we set the learning rate? This is the question. Setting the learning rate. Learning rate we have to be setting. Small learning rate converges slowly and gets stuck in false local minima. Small learning rate converges slowly only. Small learning rate converges and gets stuck in false local minima. In local minima, you will get stuck also. J of W here W. So doing like this up to here. So initial gain. Large learning rates overshoot, become unstable and diverge. Large learning rates large, if it is large, overshoot, large learning rates become unstable and diverge, not converge, diverge. Like this. Setting the learning rate. So that's why we have to be set learning rate. Stable learning rates converge smoothly and avoid local minima. If you stable learning rates, that is learning rate setting, it will be converge smoothly and avoid local minima. That is this one. Initial rate. How to deal with this idea? One. Try lots of different learning rates and see what works just right. Try lots of different learning rates and see what works just right. How to deal with this? Idea 2. Idea 1 finish. What? Try lots of different learning rates and see what works just right. Do something smarter. What will do smarter? Design an adaptive learning rate that adapts to the landscape. Design adaptive filter like that. Adaptive learning rate that adapts landscape. Adapt learning rates. learning rates are no longer fixed. Learning rates are no longer fixed. It will be temporary. Can be made larger or smaller depending on how large gradient is, how fast learning is happening, size of particular rates, and the example. Gradient descent algorithm, SGD, ADAM, ADA delta, ADA grad, RMS probe. TF implementation for this algorithm. For SGD, TF error optimizes SGD. Then for this ADAM algorithm, we have to put ADAM. ADA delta, ADA grad, RMS probe. This keras means library. This TF means TensorFlow. Tensor. Reference. Stochastic estimation of the maximum of regression function in 1952. First one, SGD. For Kingma, ETL, Adam, a method for stochastic optimization, 2014. Taylor, ETL, adult delta and adaptive learning rate method 2012. And Touchy, ETL, adaptive subgradient methods for online learning and stochastic optimization 2011. Additional details ruder.io http ruder.io/optimizing gradient descent for additional details. Putting it all together, import TensorFlow STF, putting all together, model TF keras sequential. Pick your favorite optimizer tf.keras optimizer.sgd. While true, loop forever. If false only, loop will do. True, final result. Forward pass through the network. Prediction equal to model of X. With the TF gradient, with the TF dot gradient tape as tape. This is the tape. Compute the loss. Compute loss of Y prediction. Update the weights using the gradient tape. Gradient of loss model trainable variable. Optimizer apply gradients of sheep grades model dot trainable variables. Neural networks in practice mini batches. Neural networks in practice mini batches. Gradient descent. So initialize weight randomly. Loop until convergence. Compute gradient. Update weights. W like this hidden weights. So this is the doing here this work. So gradient descent algorithm. This is the compute gradient. Okay. So can be very computationally intensive to compute. Can be very computationally